Okay, so we're starting with section 2.5 here, transformations of graphs. Now for this, this is one of the few sections that I'm going to use these PowerPoint slides for, since it's a lot of graphing and the pictures will be better if we use these slides. So this is what we're talking about when we talk about transformations of graphs. We're going to get my pointer here. All right, so we're going to look at some common functions. We want to be familiar with kind of the most common functions that we're going to see over and over. And vertical shifts mean that the shape of the graph doesn't change, but we just shift the graph either, so many units up the y-axis or down horizontal to the left and right on the x-axis, reflections through x and y-axis, and I think that's probably where we'll stop. Maybe we'll just look at this stretching and shrinking, but mostly we're going to concentrate on these first four steps in this section 2.5. So these are the common functions that we want to be familiar with, that you want to start noticing these because you'll see these more than others, and we'll have pictures of these in the coming slides. So this is a constant function where the output is just the same number, which means it's going to be a horizontal line at that y value. We'll see that. F of x is x, so the input is the same as the output. This is also a straight line. We'll take a look at that also. Absolute value of x we looked at in a previous section. X squared we looked at as quadratics in the quadratic section. Square root of x is another common function. Remember we said we're going to take the positive square root. Only the positive square root fits the definition of a function. If we took plus and minus on this, then it wouldn't be a function. It wouldn't pass the vertical line test. Again, we'll look at that. X cubed, we briefly looked at that when we were looking at symmetry with the origin, and the cube root of x. So let's look at these graphs just to see what they look like. So this is the first one, the constant function. So this is whatever value of y. In this case, it looks like it's about 1.5. So this equation of this line would be y equals 1.5. And we're interested in the same things we've always been interested with functions. What is the domain? What is the range? Where is it increasing, decreasing, or remaining constant? Is it even or odd? And that's what we're going through here with each one of these common functions. So we can see the domain here. We should have arrows on the ends of these lines, but we don't. They should have arrows to show that they're going out in either direction, giving the domain of all real numbers. The range, the only y output is that one y value at 1.5. The function is constant on its entire domain. That's what this is saying. And look at notice the symmetry with the y-axis. That shows that it's an even function. If we went through the algebra, we would see that it is, in fact, an even function. All right, this is the function y equals x. Remember, f of x is another name for y, or the output of a function. This is what it looks like. It's a straight line going diagonally through the first and third quadrants. Again, we're interested in the domain, all real numbers here. Range, all real numbers going from negative infinity to positive infinity on the y-axis. Same thing on the x-axis. It's increasing along the entire domain. Remember, the increasing, decreasing, and constant questions have to do with intervals of the domain. So we're looking at intervals of x. We see the function is increasing along the entire domain. That's what this is saying. And this is another example of symmetry with the origin, symmetry with that point 0, 0, and that shows it's an odd function. Again, if we went through the algebra, which we did in section 2.3 or 4, we'd see also that it's an odd function. Absolute value of x we talked about briefly. We looked at that graph. We said everything is non-negative. Again, domain, all real numbers. There's no negative y values, so we only get a range starting at 0 and going to positive infinity. This function is decreasing for all x values from negative infinity to 0. That's what this is saying. And then it's increasing for x values from 0 out to infinity. That's what this is saying. It's remaining constant nowhere. Looking at the symmetry across the y-axis shows that it's an even function. X squared we looked at in the quadratic section. This is kind of the simplest quadratic equation or function, now we're calling it. And it looks like this. It's a parabola where its vertex is at the origin, 0, 0. So again, we look at the important things. What is the domain? All real numbers. The range, there's no negative y's, so it starts at 0, goes to infinity. Decreasing from negative infinity to 0, increasing from 0 to infinity, an even function. Now this is the one we said we can only take the positive square root of x. If we took the negative square root, we'd get the bottom of this sideways parabola, and then it wouldn't be a function, it wouldn't pass the vertical line test. So that's why we assume the positive square root here, so that it fits the definition of a function. Domain, there's nothing to the negative side on x's, so it's just 0 to infinity. Range, no negative y's, so 0 to infinity. It's increasing from 0 to infinity. And this one is neither even nor odd. If we went through the math, we'd see it's neither even nor odd. X cubed, now remember we said negative values raised to an odd exponent remain negative, so that's why we have this downturn on the x cubed, and we had it going up on the x squared. Now it's negative values because of the odd number 3 is the exponent. So this one has a domain of all real numbers, has a range of all real numbers, it's increasing along the entire domain, and this is an odd function. All right, so these are just functions you want to be familiar with. You want to recognize them when you see them. These are the ones we're going to deal with more than others. And just like we did x squared and the square root, we look at x cubed and now the cube root. Same kind of deal here. Remember x squared, we only took the positive. We don't have to do that when it's an odd number because the negative values remain negative. The cube root of -1 is -1 and so forth. So here the domain is all real numbers along the x-axis, all real numbers along the y-axis. It's increasing along the entire domain, and it's an odd function according to our definition from 2.3 or 2.4. All right, so what we're doing in this chapter, this is what the transformations are all about. We're going to use those graphs and really just move them up or down, left and right, or reflect them about some line, usually an x or y axis. So here we're going to look at this graph function be a positive. We looked at that positive function, and or actually c here is just a positive number. We're adding a positive number to any function, and what that tells us is if c is a positive number, we shift the graph up that many units. If c is a negative, if we're subtracting a value, then we shift the graph downward. And this is a representation of that. We're starting with one of those graphs that we talked about, this absolute value of x. That's this graph here. The blue is the absolute value of x. And if we change that and create a new function and add 3 to every output, that's what we're doing here, right? We're adding 3 to every output. So 0, 0. We add 3 to that and it goes up 3 units. Every point on the blue line is raised 3 units to get the graph here in the red being the absolute value plus 3. So when you add a constant to the output of a function, like we did here, you're moving the graph up. If you subtract a number, you're going to move the graph down. And these PowerPoint slides are posted for you on D2L. You can access these PowerPoint slides for all of the sections we cover on your D2L page. All right, so this is, now notice the difference between this one and the last example we did. In this one, we're adding a number to the output of the function. Remember, y is the output of the function. We're adding a value to the output. Now in this next example, we're adding a value to the input. Okay, so when we add a value to the input, that shifts the graph to the left that many units. If we subtract a value from the input, that shifts or moves the entire graph that many units to the right. So it's a little counterintuitive. For the up and down, it was just what you would think. If you add, you go up. If you subtract, you go down. Here it's a little counterintuitive. If we add, we go to the left. If we subtract, we go to the right. And here's an example of that, starting again with one of our common graphs, the square root of x, and then subtracting 4 from the input. Right? This was the original input. Now we're subtracting 4 from that input. So that tells us we're going to take the original graph, the blue, which is the square root of x, and move every point on this graph 4 units to the right. Every point on this graph 4 units to the right to get this graph here. Subtracting 4, moved everything to the right. So that is called a horizontal shift. And then we'll look at these reflections. When we take the negative of the output, we take a function and then take the negative of the output. Again, think of what we're doing. We're taking the negative of the y. So if the y value was above the x-axis, now it's going to be below the x-axis. If it was below the x-axis, now it's going to be above the x-axis. We're changing the sign of the output, which would reflect the graph about the x-axis. If it was above, now it's below. If it was below the x-axis, now it's above. That's a reflection about x. A reflection about y, notice the difference again. Here we're taking the negative of the y value. Remember, y and f of x are the same thing. Here we're taking the negative of the x value. So if we're given a function and then we change it to, instead of f of x, f of negative x, that reflects the graph about the y-axis. The x value changes from positive to negative or negative to positive. And here's an example of that. Starting with the cube root of x graph, the blue, that's this part here going all the way through the blue. This is not a great example to use because it kind of confuses the situation, but if you notice, the blue graph is the original. We're reflecting across the x-axis, so we're reflecting across this axis. When we take the negative of x, right, we take the negative of the input, we're reflecting about the x-axis. So this part of the blue is reflected over here. Now notice, you could make the mistake and think it was reflected over here. That's why I don't think this is a great example. But this is reflected across the x-axis, this axis. So this blue part is reflected by this red part, and this blue part is reflected by this red part. So that's what's going on there. All right, vertical stretching and shrinking. Let's just go through these so we have an idea of what this is. Vertical stretching and shrinking. We're multiplying the output by a number greater than 1 or between 0 and 1. Okay, the positive and negative, notice we're only using positive values here. The negative, if it was negative, that would also involve a reflection. So we're just going to deal with numbers greater than 0 here and look at how it stretches or shrinks a graph. So if we multiply the output by a whole number, again, think about what we're doing. We're taking the output and we're making it a greater number, right? If it's greater than 1, if c is greater than 1, then we're making the output larger. And we'll see what that looks like here with the original graph of absolute value. That's the blue. And if we stretch that by multiplying the output by a number greater than 1, the stretching comes into play. Think about it as taking the y-axis and stretching it this way, which makes the graph thinner. Right? If you stretch it, it's going to make it thinner. If you shrink it, then it's going to make it wider, which we'll look at next. Okay, so here's an example of that. So here we started with the x squared, and we multiplied the input, just the input, right? The input is x. We multiplied the input by a number less than 1. So it took the original graph, the blue graph, and shrinks to make it fatter, right? To make it a wider graph. So multiplying by more than 1 is stretching the y-axis. Multiplying by a number less than 1 shrinks the y-axis. And you can have more than one thing going on at a time. Like here, we're starting with the graph of x squared. That's the blue graph, x squared. And we want to graph this whole thing, right? So there's a whole bunch of shit going on here, right? Excuse my language. We're subtracting 2, so we're going to go down 2 units. We're adding 1 to the input, so that's going to make it go 1 unit to the left. We're taking the negative of the function, so that's going to reflect it about the y-axis, and we're multiplying by a number less than 1, which is going to shrink the graph. And all of these things are done. We transform in this order. We go down 2, left 1, so you do the vertical and horizontal translations first, then the shrinking vertically, that's the 1/2 part, and reflecting is the negative part. So down 2, we take the blue graph, we go down 2 units to get this graph here, this part, then we go left 1 unit, then we shrink to get this part, and then we reflect. This is not something I'm going to hold you too much to, but there's some good examples. And again, go through these PowerPoint slides. And mostly I will hold you to the vertical and horizontal shifting. So I will hold you mostly to horizontal shifts, like we talked about here. Vertical shifts. So know a vertical shift. Know how to do a horizontal shift, what it is, what it does to the graph, reflections about the x and y, and the stretching and shrinking.